Alright, the standard normal distribution. I'll try not to butcher this too bad. But right here you have what's called the normal curve or the bell curve. In this particular one I have a very small standard deviation. So in order to understand this video you have to understand what standard deviation is, what mean is, things like that. So if you don't know what those things are, go find another video and find out what those are first. Alright, the standard normal distribution. So I have an image here of an example of that. What you also need to understand with this is that this is a frequency distribution. So, also if you haven't done frequency distributions, you might go by and check those out. And so I've eliminated some of that. So on this axis, you would have the frequency of occurrences. Yeah, frequency, probably misspell it, but there you go. So the frequency is on the left, so maybe it occurs 10 times, 20 times, 30 times, or 10% of the time, 20% of the time, 30, on up. And so that's the frequency of occurrences is on the left, and your x-axis is your mean of what you're trying to study. So this would be mu, or mean. In this case, I've made my mean 0 to make it a standard normal curve. And to the right, generally, this would be one standard deviation away from the mean, the distance of one standard deviation away from the mean. Here's 2 standard deviations. Here's 3 standard deviations from the mean. I guess you got to go all the way from the beginning, and 4, and so on. On the left, it's also the same. You got 1 standard deviation, then 2 standard deviations, and 3 standard deviations, but it's in the negative direction. It's to the left of the mean. And so that's generally what that is. Now, let's look at a situation. So for instance, in this case, you sampled 1,000 female black labs and found that the number of puppies each female has is 12. So you have about, on average, 12 puppies each time. And your standard deviation of puppies is 2 puppies. So this is a sample. We just sampled 1,000. Every black lab in the nation had a chance to be picked, and we decided to sample 1,000 of them. And so we're dealing with samples. So our x bar is 12. And our standard deviation is 2. So what that looks like in our frequency histogram, again, generally we just leave out this, but there's your frequency, how often it occurs. And let's say we graphed it and we had a bunch of, wow, that's pretty sad, but hopefully that's close enough. I can't freehand it as well as a computer can, but what we'd have then is right in the middle we have the mean, okay, which would be 12 puppies. Okay, if you went to the right, 1 standard deviation, so now we're at 14 puppies. 2 standard deviations, now we have 16 puppies, and 3 standard deviations, we have 18 puppies. Going the other direction, 1 standard deviation backwards, we have 10 puppies, 8 puppies, and 6 puppies. I'm making this up. I don't know how many puppies a black lab has. I just know they have a lot of them. And so that kind of gives you an idea of what's happening. Now, there's what's called an empirical rule. And between 1 standard deviation and the mean, 34.13% of all of the puppies will occur. In this case, all of the data will occur. If you have a normal distribution, which we're assuming this one is, 34.13% of all of our data will fall, all of our x values will fall between 0 and 1 standard deviation. Okay, if you go the other direction, it's also the same. It's also 34.13%. So together, 68% will, about, approximately, add them together, 68% of our female dogs, and I'll just put females, so 68% of our females will have between 10 and 14 puppies. And if you want more accuracy, you've got to go out 2 standard deviations. And if you go out 2 standard deviations, I'll do that in red. Now it's even, we have an even bigger spread, but now you can add on another 13.59%. That's a little more accuracy than we need here, but so 13.59% if you add on each side, if you add it on. And so the empirical rule says that we'd have about 95% within 2 standard deviations. So similarly, about 95% of our females will have between 8 and, I forgot what we're doing here. Oh yeah, 16 and 16 puppies. So 95% of our females are going to have between 8 and 16 puppies. And if you want to go 3 standard deviations out, notice it's tailing down here. So now here's 3. I'll do that one in green. That's only we're only going to add another 2.28% on each side. And if you add all the percentages up in blue, black, red, and green, now we're looking at about 99%, approximately 99%. And actually we can go a little higher there. I've always just remembered it as 99%, but it's actually even higher than that. It's 99.7% approximately for 3 standard deviations. And so that's 6 and 18. So we know that 99.7% of our females, of female dogs in our study, have between 6 and 18 puppies in this particular study. Now, the beauty of a normal distribution is if you know the data is distributed normally with this bell-shaped curve, those 3 rules always work. So about 68.2% for 1 standard deviation away from the mean, around 95% for 2 standard deviations. And if you can go out 3 standard deviations, you can get 99.7% of the data. Now, obviously, the higher your standard deviation and the closer your data is, the other way around. The closer to 0 your standard deviation is, the more clumped up your data is. Going out to that 3 standard deviations kind of works out nice. You could have a standard deviation that's kind of low and spread out, and then you could have a standard deviation that looks like this. Maybe it's really close, high, comes back down. And so the difference here is you've got a greater standard deviation here. Here the standard deviation is less, smaller. So it's going to tighten things up with a smaller standard deviation. And so that's the only difference. But it doesn't matter. If this is normally distributed, you can use that 68% rule, 95% rule for 2 standard deviations, and 99.7% rule for 3 standard deviations. So I hope this helps. You know, I'll give you probably a few more videos on this, and let me know if this totally misses the mark for you. So see you next time. Have a good one.